In this lecture, we're going to go over 5 critical topics for soil fertility. If you're unfamiliar with these topics, that's not a problem. We're going to cover each of them in quite a bit of detail. You can think of me like Charlton Heston coming down from a mountain on a Hollywood set, delivering you the real commandments of soil fertility. Now, you might notice that there's 5 critical topics, but only 4 listed. Well, that's because maybe the 5th topic has to be revealed to us, only if we do the right things. Or maybe that was a typo. I don't know. Now, before I go into these critical topics, let's have a quick overview, the big picture, Ontario soil fertility. Ontario soils are higher in pH than those found in the rest of the Corn Belt. That is going to have implications for fertilizer management. For example, we typically have much higher volatilization losses of nitrogen fertilizer when it's applied as UAN or urea compared to the rest of the Corn Belt. It just gets a lot more higher pH once you cross the border. And that has to do with our parent material, which is calcareous. So we have plenty of calcium, generally plenty of magnesium, very high levels, and this provides high buffer pH and just high pH in general. We typically have silty and clay soils. That's what predominates in Ontario as a whole. I'm not talking, of course, there will be pockets where you have much sandier areas. I mean, you can think of Simcoe with sandier areas. You can think of the Holland Marsh as a place that has pretty much muck soil. But generally, high CEC, clays, silts, and loamy type soil. So high soil fertility, these would be your class 1 to 3 soils. Average soil organic matter across the province in 2016, this is based on 10,000 plus samples from commercial labs, is 4.1%. 4.1% soil organic matter. Obviously, this is going to vary from field to field, but that's the average. On average, we don't really have any major micronutrient deficiencies in this province. Again, big picture, not really anything that really stands out in terms of a common micronutrient deficiency, but they are commonly added as insurance, especially if they're not expensive. So a classic example is boron with canola. I mean, boron is found in borax. You can buy borax at a grocery store, and you can add it at whatever, half a pound, 1 pound an acre. It's not very expensive. Sometimes there's a response, often there is not, but it's so cheap, farmers will add it often as an insurance, growing canola in Ontario. And again, the micro is important here. Very small amounts, if any, are needed if there is a deficiency. And so typically micronutrients can be applied, if needed, as a foliar application. Those are usually more expensive, but because you need such little amounts of micronutrients, you can apply it as a foliar. You can apply something like P or K or N as a foliar, well, let's say nitrogen as a foliar fertilizer, but the crop needs a lot more nitrogen than it does a micronutrient. And so the amount of nitrogen you can safely apply to a crop compared to crop uptake needs is like, 1 or 2%. Whereas, with boron, you can apply foliar boron, and that's, 100% of plant needs. On average, P and K levels depend on management. And that's like the past 20 or 30 years. Was that field getting manure? Was it in forages where you were removing crop biomass year after year? Generally, old hay fields that have been hayed for 20 years, they will have potassium deficiencies. That's quite common because you're removing so much of that whole biomass, not just the grain, and it's the stem and the leaves and the stalk that have quite a bit of potassium. Nitrogen. The one thing I'll say with nitrogen is we have high soil organic matter levels. We typically get quite a bit of mineralization in the spring. Depending on the crop, often you need to supplement, again, depending on background fertility, manure, whatever. But we have little fall-applied nitrogen. And so we have less issues with leaching compared to the rest of the Corn Belt. So in previous classes, you've probably heard about nitrogen leaching, and how that causes huge problems in terms of groundwater and surface water contamination of nitrogen. That's a much bigger problem in the United States where they apply nitrogen in the fall. Here we apply nitrogen typically in the spring. Almost all of the nitrogen is applied in the spring, around planting or after planting. not a whole lot of leaching. Sulfur. This was covered in Q&A, but overall, we have less free sulfur deposition from acid rain, and so there's ongoing research to see if there's consistent deficiencies and therefore consistent responses to supplemental sulfur fertilizer in the province. The last thing I'll add here is that Ontario soils tend to have more topography and more stones than, say, soils in the Midwest. Okay, it's a lot stonier and rockier. Sometimes there's some parts of the Midwest where you can't really find any stones. That's just not the case in most of Ontario, and we're dealing with a little bit more topography than folks, say, in the Midwest or in the prairies. Okay, so 5,000-foot view, Ontario soils are very diverse in terms of soil textures, organic matters, not so much parent materials, generally calcareous parent materials, but there are exceptions in some parts of the province. So here are some common exceptions in field crop production. You can get eroded knolls on a field due to tillage erosion. We talked about that in an earlier lecture. And those eroded knolls are typically high pH because that B horizon, that parent material, which is calcareous can buffer pH, so it raises pH. It makes it more basic, the soil solution. That B horizon becomes the A horizon, so that crop is growing in a very high pH environment. High pH environments will restrict nutrient availability. They will, for example, phosphorus will become almost completely unavailable. It'll precipitate out of the soil solution. It'll become unavailable to crops. You also have low organic matter in those eroded knolls, so you have less mineralization of nitrogen and sulfur. So that is a problem, say, within a field. On sandier soils, instead of high pH knolls, you can get low pH knolls because you don't have that high levels of calcium or other buffering agents that can increase pH. You slowly get over time an acidification of that knoll because it's just mostly sand, low organic matter. And so as that soil acidifies, again, some nutrients are going to become unavailable to plants. And that means that even if you apply the nutrient that is limiting, right, based on a tissue test, if that fertilizer is applied to the soil, it'll still be unavailable to the plant. Okay, so that's something to be aware of. Next, we have muck soils in this province in certain areas. Holland Marsh is a big one. The other really big one is Northern Ontario. So when we think about, if you've heard about this term, the Great Clay Belt or the Little Clay Belt, those are clayed soils, but on top of that clayed soil is 6 inches of organic matter. And so that would be considered, you would call that a muck soil. Over time, that muck soil is going to get burned off over time, and so it'll become more and more clayed. But these soils are managed in not a completely different way, but they have their differences compared to what we'll generally be talking about today. So our first critical topic that we're going to cover is how fertilizer recommendations are made and implications for high-yielding production environments. Should we be revising or rethinking current fertilizer recommendations as yields of our major field crops get higher and higher? So first, let's talk about how are fertilizer recommendations constructed, and it starts with your soil test. Once the soil test is made, it is only testing for plant available nutrients. A classic example: the total amount of nitrogen in an acre of field soil, the top 6 inches, is going to be in the thousands of kilos or the hundreds of kilos of available nitrogen or pounds. But we're only testing for how much is plant available. Now, to be plant available, that nutrient has to be dissolved in water. As I mentioned previously, soil pH has a huge impact on the availability of nutrients by allowing them to precipitate in and out of the soil solution in that soil water. So soil scientists have to be able to first extract the nutrients that are plant available. And different soil tests are better suited to different soil pHs, again, because we need that water or dissolvable nutrient form. So in the Midwest, soil test phosphorus is measured with the Malick or Braze test. In Ontario, we typically use the Olsen or sodium bicarbonate test that has to do with the pH. So next, they'll get that soil test value, and then they're going to give you a recommendation to fertilize or not to fertilize, or how much to fertilize. So the background data set being used to provide those recommendations to you are based on hundreds, if not thousands, of field tests, usually at the farm scale, on farm testing of fertilizer response or nutrient response trials, where they also measure the background levels of that nutrient to come up with a probability of, based on this soil test value, is this responsive or unresponsive site, and if so, how much nutrient should be applied. So here is phosphorus, for example. On the x-axis here, different rates of fertilizer P applied to corn, and then you have corn grain yield on the y-axis. So from the top to the bottom, we have soil test levels of 9 ppm, 15, and 23. And you can see how on those lower soil testing fields, you have a much higher response. And then when you get to 23 ppm, there's no response to applied fertilizer. And so this hundreds of field sites or field experiments like this are used to construct give you probabilities of, for a given soil test value, is this responsive, unresponsive, how much to apply. Now these results do not apply to small levels of starter fertilizer. So small levels of nitrogen, phosphorus, potassium that are applied close to provide a starter or pop-up effect. And again, going back to previous lectures, Ontario soils are quite cool around planting. Root growth is slow, so you might have high soil nutrient levels in the soil, but it's not necessarily available to that plant. So by placing a small amount of that nutrient close to the seed, you can increase early season vigor and growth, but these are not high amounts of that nutrient. So even in high soil test fields, there's often a benefit to applying that nutrient, small amounts, close to the seed. So the empirical data sets used to provide fertilizer recommendations, these experiments were done in the 70s, 80s, 90s. Even if the recommendation came out in 2000 or 2010, they're using much older, field trials to come up with their recommendations. And so there's a valid question of, in high yielding production environments in the past 20 years, are these recommendations, do they need to be revised upwards? And there's a couple of strong reasons why one would suspect that. It makes logical sense why you might need to do that. First, as yield potential increases, nutrient uptake needs also increase. Now, they increase differently for different nutrients. For example, corn needs 18 kilos of nitrogen per 1,000 kilos of grain. Sulfur, you need about 1.6 kilos of sulfur uptake for 1,000 kilos of grain. So the increase in nutrient demand as yield goes up depends on the specific nutrient. You'll need a lot more nitrogen for every yield increase increment compared to sulfur. That's true for many other nutrients, but that's the general principle. Number two, yield response curves are going to change their shape. So especially as yield potential goes up at those higher yield levels, the shape of a response curve will also shift up. And you can see here, maybe if those yield response curves shift up, then that optimum applied P is going to go up as well. So those two things are important. The next thing to mention is that nutrient removal rates from the soil will increase as well. Okay, grain is the most nutrient-rich part of that plant, and so as you harvest more of it, you're harvesting more of all the nutrients, all essential nutrients, and that has important implications for fertility in a specific across fields. And we'll talk about that in a second. So let's go back to that original question. Should we be revising upwards our recommendations of sufficiency, deficiency, our critical values, or updating rate recommendations? I think there is some evidence to suggest that we should be. So this is this is data from Indiana, published in 2017, where they compared corn ear leaf nutrient concentrations at silking in modern high-yielding production environments compared to what the state recommends is the minimum critical sufficiency test level. So typically what you would do is you'd go out in a field and collect some ear leaves from corn right at silking. You would measure nutrient concentrations, and if you were below a critical level, you'd be deficient, and there would be a recommendation to fertilize. So here we have data for nitrogen on the left, nitrogen concentrations in the ear leaf, and on the right is sulfur S. And this is on the x-axis, nutrient concentrations, gram per kilogram. You divide by 100 to get percentage. So the green line is the state recommendation, Indiana State, And that was, again, based on empirical data from the 70s, 80s, 90s. And then the little black dots you see are actual values from more recent field trials, higher yielding production environments. Should we be revising our critical tests upwards? For nitrogen, I would say probably not, or by very little, if any. This is, let's call that 3% or 30 grams per kilogram. There doesn't seem to be a huge yield response above 3 grams per kilogram ear leaf concentration in nitrogen. And so I think that sufficiency deficiency level is probably still valid. I'm just eyeballing it here. Looking at sulfur, I think we need to revise that upwards. Okay, we probably have to go from 0.15 or 0.16% maybe to 0.2% or 0.21 or 0.22. You can just see that there's so much of a higher yielding. There's a lot more higher yielding corn now, and those higher yielding corn typically have a higher ear leaf sulfur concentration. So I think maybe there's a case to revise it. Again, eyeballing it. The next important thing I want to mention is as yield levels get higher, nutrient removal rates get higher. And so you need to start paying attention possibly to nutrients across the field based on removal rates, yield levels across the field. This is data I'm presenting from master's student Allison Bailey's thesis research. This is a 10-year-long trial on a 4-acre field. You can see a photo of it there. At the Elora Research Station, you can see some data. Basically what we did is across this field, we applied 6 nitrogen rates long-term, so year after year over 10 years. So we applied either 30 kilograms of nitrogen per hectare year after year, 58, 87, 145, 208, 260, year after year. Now the Ontario OMAFRA N rate recommendation is 145 kilograms of nitrogen per hectare. So we can say, at the 30, 58, 87 levels, we're probably deficient in nitrogen. We're probably getting lower yields. We're nitrogen limited. And then at the 208, 260, and 145, we're high in nitrogen. We're going to have high yields. And so we're creating a gradient in terms of yield levels across this field and a gradient in nutrient removal rates as well. Now, we applied P and K every year based on a soil test, but it was a uniform rate. We didn't apply more P or K in the 145 or 260 than we did in the 30 kilogram per nitrogen per hectare treatments. We applied it uniform across the field, ignoring nutrient removal rate differences. Okay, so what happened after 10 years to the nutrients that we were just blanket applying, like your PK? We didn't apply any calcium or magnesium, but we also looked at what was going on there. So first, let me just show you, this is yield, average yield across the 10 years at the 6 nitrogen rates. And you can see, yield did go up. So at the lower level, we were averaging about 5 tons per hectare. At the high level of nitrogen, we were averaging about 8 tons per hectare per year of yield. And therefore, that stuff's getting removed from the field. So we have differences in nutrient removal across those plots, getting different N rates. And let's look at what happened to our soil test phosphorus and potassium, magnesium. Again, we were applying OMAFRA recommended rates of P and K blanket across the field based on a soil test. We're not stratifying or sampling. We're just taking a couple of random soil cores across that field and applying a blanket rate. Look at what's happening to phosphorus and potassium. Okay, in the 30 kilogram per N per hectare per year. So very low yields because we're not applying much nitrogen. We have much higher soil test phosphorus and potassium compared to, just go to the bottom there, 260 kilograms of nitrogen per hectare per year, which is where we have very high yields, like double the yields. Okay, so going from almost 33 ppm to 25 ppm, 160 ppm to 145 ppm. These are all sufficient, based on a soil test, sufficient levels of phosphorus and potassium. But you can imagine that over a longer time span, if you have areas that are just consistently higher yielding compared to others, nutrient removal rates are going to differ, and therefore the rate of phosphorus and potassium extraction or removal are going to change as well. And so that's going to be important over the long term to keep in mind in terms of soil sampling and for our more strategic or tactical phosphorus and potassium placement. If we look at magnesium and calcium, we have very, very high levels, and they didn't actually change. We have a small change in pH and cation exchange capacity. I wouldn't worry, magnesium, calcium, not to worry. It's really phosphorus and potassium where we're seeing this big difference. The next critical topic is that the status of a crop in terms of sufficiency or deficiency in a particular nutrient, that determination is due to the interaction between soil, crop, and weather. So it's not just based on how much nutrient is quote unquote available in the soil. And let me explain what I mean by that with the following slides. First, nutrient uptake by a crop, no matter what crop it is an energy consuming process, right? It takes energy to take up nutrients. Okay, unlike water, which flows in passively, nutrient uptake is an energetically costly process. And crops are not quote unquote dumb. They're not going to just keep on taking up nutrients if they don't really need them. And so what makes a crop need nutrients? It's crop growth rates. There's hormone regulation in that plant, hormone signaling. So if the shoots are growing, if the leaves are growing, the above ground biomass is growing, it's going to send signals to the roots. We need to take up nitrogen, we need to take up phosphorus, whatever. This is a process controlled by the crop. So you can pound a crop with nutrients, pound it with micronutrients, macronutrients. If the crop doesn't really need it, it's not going to take up very much. Sometimes we get what we call luxury uptake, which is nutrients that are taken up when the crop doesn't really need them, but it's usually not a large amount. Crops take up nutrients in proportion to their needs, and so faster growing crops are going to need more nutrients. Okay, so let me break this down a little bit. Okay, so as I mentioned, faster growing crops take up more nutrients for two ways. One is that hormone signaling I was talking about earlier. So just fast growing crops are sending hormone signals to the roots like, hey, we're really growing fast, like we'll take up nutrients, spend some energy taking those up. The other thing is that faster growing crops by definition are photosynthesizing more. And if they're photosynthesizing more, they have more energy available. Because remember, nutrient uptake is energetically costly. And if there's not enough energy to support nutrient uptake, that crop will not take up nutrients, even if it's somewhat deficient in them. So faster growing crops have lots of energy, lots of photosynthesis that they can share with the roots to help power up that nutrient uptake. Okay, so crop growth rate is one thing. The other thing is root system size, and you could call root system structure. So overall, larger root systems means that more nutrients can be taken up. And so, if you're exploring more of that soil area with a more fibrous root system, let's say, or a deeper rooting system, well, there's more nutrients that can be taken up by that crop. That's especially important for immobile nutrients, things like phosphorus that don't travel very far, that are taken up primarily by diffusion. There you want a larger root system is going to really help increase availability of that nutrient for crop uptake. If you have a smaller root system, all things being equal, there's just not as much nutrients available to that particular plant. The other thing I'll talk about is the root system structure. So we can talk about fibrous root systems, tap root systems. Generally, or deeper rooting systems, generally more fibrous rooting systems can take up more nutrients under drought. So remember that some nutrients are transported to the root via mass flow, things like nitrogen. As that soil dries out, nutrients are going to become less available. We'll talk about that in a second. But more fibrous root systems have the ability to take up those nutrients better in drier conditions. Next is energy allocated to the root system during grain fill. So all things being equal in cereal crops like your wheat, your corn, your oats, include even brassicas like canola. During grain fill, nutrient uptake always declines. And again, the reason why is because there's not as much photosynthesis, not as much energy or sugar available to those roots to power nutrient uptake. That crop is putting all that energy into the grain fill, into those grains. So we always have a decline in nutrient uptake during grain fill with almost all of our cereal crops. And that has to do with reduced photosynthate supply to those roots. So again, it's a participatory process, this nutrient deficiency or sufficiency. I'm just going to show you again, as a scientist, I want to show you a little bit of, or give you some studies to back this up. I mean, there's dozens of studies that back what I've been talking about, but here's one that's very, very new, came out this year. This is a cool study. So this just came out a couple months ago. It's a meta-analysis, 679 experiments across the USA and Canada. They looked at corn yields in unfertilized without nitrogen fertilizer. They said, if you're not fertilizing with nitrogen, what determines corn yields? So as you would expect, right, these yields were low, they were limited by nitrogen, and so soils with generally higher organic matter had higher yields. Soils with more, you would say, not finer textures, but your silty and your loamy soils typically had higher yields because they could retain nitrogen a little bit better than sandier or clayed soils without losses. But also, one of the variables that most strongly explained corn yields when no nitrogen fertilizer was applied was sunlight around the critical period bracketing silking, right? It's radiation essentially during that critical period. And why? Well, going back to what we were talking about, it's a participatory process that governs nutrient deficiency. So if you have, for a given level of soil nitrogen, if you have a crop that is getting a lot of radiation, so that means it's growing quicker, it has more photosynthesis to provide to the roots, so those roots can go, they have lots of energy to take up nutrients, that crop will take up more nutrients, okay? All things being equal. And so even though we have you're not turning the crop from deficient to sufficient just with some extra sunshine around silking. But what it's doing is it's alleviating it a little bit. Again, because we have that more energy for the roots, okay? So it's this participatory process. The next reason why nutrient deficiency and sufficiency should be thought of as a participatory process is because of the effect of soil moisture that is, largely determined by rainfall and precipitation on nutrient uptake rates, almost independent of the availability of that nutrient in the soil. So soil moisture status is going to determine, for many nutrients, how easily accessible they are. So remember that the way that nutrients arrive to the surface of the root for uptake, that can happen in three ways, and different nutrients have basically different pathways that are more important. So nutrients that are very easily dissolved in water typically arrive to the root surface via mass flow. That's, movement of water in the soil at the scale of centimeters to meters. As soil moves through that soil profile, it's bringing with it dissolved nutrients that will hit roots, and the roots will take up those dissolved nutrients in the mass flow water. As soil dries, we get less mass flow, and nutrients that are dependent on mass flow to get to that root, those nutrient uptake rates will decline. So there's been a lot of interesting research recently showing this in corn, that as the soil dries in corn, even before we get drought, even before that corn crop gets some drought, experiences droughts and starts showing visible signs of drought, it is going to have lower nitrogen uptake. So even before that drought becomes apparent, nitrogen uptake rates are already reduced. Because remember, drier soils, less mass flow, less nutrient uptakes when those nutrients are dissolvable or can dissolve in water. And so that's very important. When we're talking about root interception and diffusion, we're not as dependent. The nutrients that really rely on root interception and diffusion, those would be things that are very immobile in the soil, not easily dissolved. Things that need to come off those cation exchange sites. That would be your calcium, your potassium, your phosphorus, things that travel at most millimeters in the soil, not readily dissolved. For those nutrients, what really matters is going to be and you can see here the relative size of the zone of mass flow and interception and diffusion. What really matters here is the size of that root system, particularly those fine root hairs. And so anything a farmer can do to increase the size of that fine root system is going to increase nutrient uptake of those more mobile nutrients. And so maybe you're thinking, well, hey, aside from maybe picking different genetics, how can I, increase the fine root system of my crops? And one way you can actually do that is by promoting these AMF, arbuscular mycorrhizal fungi, AMF fungi. These are fungi in the soil that form symbiotic relationships with plants. They'll inoculate or infect the plant roots, and in exchange for energy, for photosynthate carbon from photosynthesis, they'll provide those crops with nutrients, and this is particularly important for phosphorus. And it's actually quite common in corn in Ontario that in no-till soils you get higher early season phosphorus uptake because tillage can disrupt AMF. Right, they're basically like these fungal networks in the soil. Tillage will disrupt those, and it takes some time for those AMFs to become reestablished again. And early in the season, while they're establishing in the no-till soils in Ontario, where there's no tillage, obviously, those AMF are able to really resume activities once those corn plants are seeded early in the season. You get higher phosphorus uptake in those no-till soils. And this is data from a really interesting study with soybean. This is from Brazil, but I'm sure the results pretty much hold here in Ontario, where they fertilized soybean with phosphorus fertilizer, phosphate, or with AMF, arbuscular mycorrhizal fungi. So I guess this is a seed treatment, a biological, and they combined both. So they did the fertilizer and the AMF. And if you look at total biomass in the control versus the other treatments, total phosphorus uptake, you can see that the best treatment was when you combine the fertilizer with those arbuscular mycorrhizal fungi. And again, it's going back to increasing the fine root system of that crop by allowing even more AMF to be to inoculate those soybean plants. And so you're taking up that fertilizer much more efficiently. Now, the other interesting thing to note here is that you're also increasing nitrogen nutrition in that crop. They're not fertilizing with nitrogen, they're just fertilizing with phosphorus and adding AMF, but you can see that you're also increasing total nitrogen. And so what's going on here? Well, the phosphorus uptake is making that nitrogen fixation more efficient. And that's another important, when we talk about nutrient deficiencies, we get these kinds of synergies between different nutrients where in a crop like soybean, phosphorus will make nitrogen fixation in those rhizobia way more efficient. And so you'll also usually get a nitrogen uptake boost when you fertilize a soybean crop that's deficient in phosphorus with phosphorus fertilizer. And same with AMF. You typically get an increase in nitrogen fixation when a legume crop is inoculated with AMF, arbuscular mycorrhizal fungi. All right, let's now talk about the economics or environmental consequences of nutrient management. So we'll talk about economic profit, environmental losses, and we're going to start with the introduction of the 4R nutrient stewardship framework, which I imagine most of you have heard of, but I think this is going to become increasingly prevalent as a framework in terms of decision making to guide on-farm nutrient management decisions. It's certainly being rapidly adopted by the industry, and so many agribusinesses in Ontario have really enthusiastically adopted the 4R certification, as well as CCAs in Ontario. There's now an option to get an additional certification in terms of 4R nutrient management. So let me first kind of describe what this is. This might be, again, review for some of you. This is basically an industry-led framework. It was probably the main charge was by the International Fertilizer nonprofit, so the Fertilizer Institute, the International Plant Nutrition Institute, these large organizations that are basically global, supported by the global fertilizer industry, because this is a framework that basically benefits all fertilizer manufacturers. Okay, so it's actually trademarked, this 4R kind of nutrient stewardship. The logo is trademarked by the Fertilizer Institute, again, a large nonprofit industry-funded organization. So 4Rs, there's 4Rs. They're very, very simple, right? It's applying nutrients in the right source, the right rate, in the right place, at the right time. Okay, we'll go into that in detail, but it's basically a framework that is in accordance with very basic fundamental principles of science in terms of plant mineral nutrition, soil fertility, soil science, and agronomy. So nothing's very woo-woo. It's all very grounded in science that has been around for 50 plus years. Now, this framework is a framework, which means it does not give hard and fast prescriptions. It's a scientifically backed framework to guide local on-farm decisions, and it accounts for the reason why there's no hard prescriptions is it's global, right? This is not Ontario specific. It's global, this framework. So it has to account for local or regional differences in climate, soil type, technologies, and economics. Now, here's some quotes from Dale Cowan, who's a certified crop advisor in the province, the head agronomist for a fairly large agribusiness in Ontario. I attended a talk that he gave on 4R nutrient stewardship, and this is what in the presentation. He said that what 4R allows is for local site-specific decision-making, which is a better approach than a rigid regulatory framework. So instead of saying prescriptively, this is what you ought to do, what 4R does is provides an option, scientifically backed management choices to the farmer. And lastly, he says, and I thought this was interesting, that right, in terms of the 4Rs, is not a scientific term, it's an ethical term. And I think I don't want to put words in anyone's mouth, but I think what this is getting at, this statement, is, some of these 4R decision options are not necessarily going to be the most profitable. And so in terms of stewardship, you have to think in terms of ethics, not just the bottom line. Okay, and we'll talk a little bit about that later in this course, or in this presentation. So this 4R framework breaks things down very simply in terms of the right rate, the right place, the right source, and the right time. That's what you need to do to optimize your fertilizer or your manure applications, right? Source, rate, place, and time. So what do these things mean exactly? I'll just give a quick overview. So in terms of the right source, are you using a slow release formula if that's required, or are you using a quicker release formula if that's more suitable? If you're using fertilizer blends, are you making sure you're not over applying one particular nutrient if you have multiple nutrients in a fertilizer blend? If you're applying, say, nitrogen in an area that's very susceptible to loss, are you maybe using a urease or a nitrification inhibitor? And that would probably cover most of that source. There's other aspects as well. The right rate, you're basically applying that fertilizer, you're matching the amount of fertilizer applied to the actual nutrient uptake needs of that crop. So you're optimizing that rate to make it appropriate. Now, this is a much easier said than done. You would have to account for what's your crop nutrient demands, or what's your expected crop nutrient demands, how much of that nutrient is already in the soil and will be supplied by the soil, so it doesn't need to come from that fertilizer. Are you calibrating your equipment so you're not over or under applying inadvertently? Taking into account things like crop yield goals, or even, we can go into spatial application, variable rate, where maybe you're not applying as much in lower yielding spots, or in an area that is deficient in nutrients, you're applying more than in other areas. So that's the right rate. Right place has to do with, we can talk about spatial variation. So across a field, are you spatially applying? That's one possible aspect of the right place, applying it where it's needed. But also, more fundamentally, the placement of that nutrient in the soil profile. So is that fertilizer being placed in the root zone? Is it protected from environmental losses? And are you considering placement that can minimize loss and maximize crop uptake? And that's going to depend on things like what crop type's being grown, what's the soil type, what's the climate and weather. So, just a classic example is very little fall-applied nitrogen in this province because we tend to have high overwinter losses. In other areas of the world, especially areas that are drier, fall-applied nitrogen can be a more successful strategy. All right, so in terms of the right place, or or that would probably be more of a right time, but yeah, the principle still stands. This is all going to be very site-specific or region-specific. So now let's go to the right time, which is the last of these 4 R's. You're placing fertilizers when they are most needed by the crop. You're applying that fertilizer when it's going to be taken up by the crop. And that's important for 2 reasons. Number one, you don't want that crop to be stressed, so that nutrient has to be applied at or before it's demanded by the crop. Number 2, you're minimizing residence time in the soil, reducing the risk for environmental losses when nutrients are applied when they're about to be taken up. So again, going back to this fall applied versus spring applied, the right time, this framework suggests that at least in Ontario, you would not want to apply nitrogen in the fall, right? Because there's just too high of a risk for large losses before it's going to be used by the crop. And so that's the right time, matching application timing to the needs of that crop. I think this 4R nutrient stewardship framework is going to become increasingly important. It's increasingly adapted by industry. And like I said, there's for certified crop advisors, there's a 4R nutrient management specialty, which is a separate written test. In any case, one thing I wanted to draw your attention to is that in Ontario, unfortunately, the most economically harmful loss pathways are not the most environmentally harmful, and the reverse is true. The most environmentally harmful loss pathways are not the most economically harmful for the farmer. So initially you might think, well, hey, there's a win-win here, right? You have lower nutrient losses to the environment. That means more is staying in the field or being taken up by the crop. That's a win-win for the environment and for the farmer's bottom line. But the fact is the nutrient losses we're most concerned about are actually quite small and not that economically important from a farmer's perspective, whereas the main loss pathways that a farmer would be concerned about, where you can lose large amounts of nutrients, those are not really the most harmful environmentally. So I'll talk first about nitrogen and then phosphorus. So with nitrogen, we have this leaky pipeline model of nitrogen cycling in a farm field. So you get fertilizer and manure inputs. That will eventually lead to crop production and crop nitrogen uptake. But before that happens, or while that's happening, we have all these loss pathways, this leaky pipe, so to speak, where in Ontario we can get some leaching and runoff. Most agronomists would argue that in most years, on most soil types, this is not a huge concern in Ontario because, again, nitrogen is generally not fall applied. If it was fall applied, then this would be a much larger concern. But leaching and runoff, not so much. The main loss pathway would be denitrification, so N2, as well as volatilization, NH3. Okay, and again, NH3 or ammonia volatilization, that's covered in your soil science courses. Ontario has relatively high pH soils. Those high pH soils more vulnerable to ammonia loss. Denitrification and ammonia volatilization are not super environmentally harmful. I mean, dinitrogen or denitrification is not harmful at all. Most of the air in the atmosphere is nitrogen gas. But the main concern here is nitrous oxide, that N2O, which is a very potent greenhouse gas. At most, a farmer is losing 1 to 2 pounds of nitrogen per acre through N2O. Whereas with ammonia volatilization, they can easily lose 30 pounds of nitrogen in a day if it's the right conditions and say they're broadcasting urea. With N2 gas denitrification, again, easily 30-40 pounds of nitrogen. So you can get, you can say there's an economic argument to reduce those kinds of loss pathways when you're losing 30, 40, 50, 60 pounds of nitrogen an acre to denitrification or volatilization. But with nitrous oxide, 1 or 2 pounds, that's a tough economic argument to make, which, we're not talking about ethics here, just purely from an economic argument. Managing to reduce nitrous oxide emissions, there has to probably be some sort of subsidy, I imagine, to really push management to reduce nitrous oxide. Now, the good thing is, or hopefully, if you manage to reduce ammonia volatilization, you'll also reduce N2O emissions. That's a hope, but the fact is, the economic argument for reducing N2O is not strong, while the environmental argument is very strong. Next, let's look at phosphorus. Okay, so I'm sure in previous courses you've heard about phosphorus pollution in the Great Lakes, causing essentially algae blooms in the Great Lakes. Long story short, the Great Lakes that surround border the U.S. and Canada here, they're very phosphorus limited, their primary productivity. So if you add some phosphorus, then things are going to start going. And so with phosphorus runoff from non-point source pollution, primarily from agricultural fields, you will get fairly large algae blooms because of this, phosphorus fertilization of the Great Lakes. This, I won't get into the details here, but that's a major problem, especially in certain years, and it's something that environmentally many stakeholders want to reduce. Reduce this non-point source pollution of phosphorus from farm fields. Now, that phosphorus can run off via surface erosion, or that phosphorus can be dissolved and exit via tile drainage. Now, if we ask on a given hectare of land, how much phosphorus is being lost per year? Okay, it's about, this is data from Ontario that showed 0.3 to 0.5 kilograms of phosphorus per hectare per year. Other studies show a little bit more, maybe 2 or 3 kilograms of phosphorus per hectare per year. But again, there's not a strong economic argument. I'm not talking about ethics, economic, to really invest energy, effort, capital into reducing phosphorus losses. Okay, there's the economic argument is not strong because it's such small amounts, right? Very small amounts of phosphorus. And so that's why I think, going back in his presentation, Dale Cowan said this is an ethical framework, or it's an ethical choice as well, because at some point it comes back to nutrient stewardship and it not necessarily the bottom line. All right, wrapping up here, I want to go back to the economics, and I'm going to specifically talk about nitrogen management, nitrogen fertilizer management in corn, using, again, data from that long-term nitrogen rate trial that I talked about earlier, showed you some data from Allison's thesis. Okay, so nitrogen is a major variable cost for corn production. It's like the number 2 biggest input in terms of the cost of production. And so getting the right rate is really important. You don't really want to over-apply, and you don't really want to under-apply. Okay, so the right rate is going to depend on things like how much nitrogen is being supplied by the soil via mineralization, how much nitrogen is being demanded by that corn crop, so what's its yield potential. And again, going back to the study, this study that I showed you earlier, it was done on a 4-acre field. So we're not talking about a really big field. But economically optimum N rates, I won't really worry about how we calculated that, but our economically optimum N rate varied from 140 to 260 kilograms of nitrogen per hectare. So over a 10-year period, and you can see each year is its own yield response curve to nitrogen. This is side dress nitrogen at V6, optimum nitrogen rate, the most profitable one, 140 to 260. So over 100 kilogram per nitrogen per hectare swing, like 100 pounds of nitrogen per acre swing over 10 years. Okay, so lots of variability. And so you might think, wow, it's going to be very difficult to, you could say, maximize profit in every year because your nitrogen rate's changing so often and so quickly. We need to use, precision ag approaches and lots of fancy technology. I would say, let's hold on for a minute. Certainly from a 4R nutrient stewardship perspective, absolutely. You do want, you want to do your soil tests. You want to do PSNTs, your pre-side dress nitrate tests. Absolutely, you want to do those things. But let's convert these crop yield response curves to profit response curves. And what you see here is your net return to fertilizer at different fertilizer rates in each of those 10 years. And what we see is that profit response is actually quite flat in every year. What that means is that, yes, we have one maximum MERN, which is most economical rate of nitrogen, one profit maximizing rate. But you can be plus or minus 25 pounds an acre around that rate and still get within $10 an acre of max profit. In other words, you don't need to be super specific with your N rate, super precise, to get pretty close to maximum profit. So here you can see in green, this is where relative MERN loss is less than $10 an acre. So you can see that in every year there's a fairly wide range of nitrogen rates that gets you within that $10 an acre of maximum profit. In fact, you could draw a line, as I do, say 180, 160 kilos of nitrogen per hectare, and that would get you within $10 an acre of max profit in 8 out of the 10 years. You can see I've circled 2 out of the 10 years where economically optimum N rates were much higher, and so you'd be under applying. And then I would say, again, from a nutrient stewardship perspective, there's that 1 year where your most economical N rate was very, very low, and you're over applying by a considerable amount in that year. But aside from that very low year and those 2 very high years, the other years, your 70-80% of your years are falling within that range of you're getting within $10 an acre with your standard rate of 180 or 160. So this is all to say that I think the goal of nitrogen management, certainly spatial variations are going to exist across a field. Certainly you should do your soil tests, but really the lowest hanging fruit to improve nitrogen management is going to be just identifying those years. Are you in a very high yielding year? Are you a very low yielding year, or a year where you don't need as much nitrogen? Are you in a year where you need more than normal? Because in most years, there's one rate that'll get you in that ballpark. So it's really about identifying those extreme years. And I think that's going to be the best, lowest hanging fruit use of precision ag technologies. Okay, so the last of the 5 critical topics for soil fertility is looking at the long-term effects of fertilization on soil properties. And I'm going to restrict this discussion specifically to nitrogen fertilizer as opposed to any other nutrient. Because it's nitrogen fertilizer that probably has the most contention in terms of its long-term effects on what you could call soil health. Although I would argue that that's really too vague a term. We're going to focus only on soil organic matter. So this is how nitrogen fertilizer affects on soil organic matter or soil organic carbon shakeout. Nitrogen fertilizer can increase yields. When you increase yields, you increase total stover and residue. When you increase residue, you're increasing the carbon inputs into that system, into that farm field. When you increase carbon inputs of residue into that farm field over time, we're not talking about 1 or 2 years, we're talking about decades. Over time, we're going to increase soil organic matter and soil organic carbon. So on one hand, you can say nitrogen fertilizer increases soil organic matter over time by increasing yields. On the other hand, some argue that actually nitrogen fertilizer, quote unquote, burns through soil organic matter and therefore is detrimental. So we know that there's billions and billions of microbes in the soil. If they would like to eat that organic matter. So on one hand, they are themselves organic matter, those microbes, but they will chew through organic matter and belch out carbon dioxide. That's the mineralization process. They'll belch out carbon dioxide and release other nutrients. So one argument would be that, well, microbes in that soil are limited by nitrogen. In other words, they would chew through that soil organic matter, but they don't have enough nitrogen to do it. And so by minimizing nitrogen inputs, you're slowing microbial growth, you're reducing the mineralization of organic matter because those microbes are chewing through that soil organic matter because those microbes are limited by by nitrogen. And so if you fertilize that soil, you give those microbes effectively a bunch of nitrogen. They're going to synthesize proteins because that's what nitrogen will do. They'll synthesize those proteins and get those enzymes available to actually chew through and decompose that organic matter. So you could argue that nitrogen fertilizer reduces soil organic matter. And so what is the overall effect nitrogen fertilizer on soil organic matter, which is a key component of soil health. This question was assessed in that same long-term study. This is research done by Alison Bailey, current master's student at the University of Guelph. So she looked at a bunch of soil properties. Earlier, I showed you data about soil potassium, phosphorus, magnesium, and calcium. Now I'm going to show you impact of on soil organic matter. And so just to recap, this is 10 years from 2009 to 2018, applying the same nitrogen rate year after year in the same plot over 10 years. So that plot either got 30 kilos of N all the way to 260 kilos of N per hectare in, equivalent in that plot. And again, the recommended rate in this area, according to OMAFRA guidelines, the corn calculator, is 145 kilos of N per hectare. And so we have very high and very low rates. So this is average yields, and at each of those 6 different nitrogen rates. And you can see this is a responsive site. At the low end, when we have like low rates of nitrogen, we got 5, 6, 7 tons per hectare, and at that higher rate, we got closer to 10 on average. Now, when we're not looking at grain yield, we look specifically at stover. That's basically the residue return. It's a very similar story. We have, at the low end, we have about 5 tons per hectare or megagrams per hectare stover return. And at the high end, at those higher end rates, we have, closer to 8 tons per hectare stover return. So we have significantly more carbon residue inputs at those higher end rates. So residue was returned year after year. No one touched the residue. It was just stayed in the plots as is. And they measured soil organic carbon, which is related to soil organic matter. In fact, about 40% of soil organic matter by weight is soil organic carbon. And in the scientific literature, we talk about organic carbon, not organic matter. In any case, we measured soil organic carbon in 2009 from the 0 to 20 and then 20 to 60 centimeter soil profile. That was repeated in 2019. And they took, 300 plus soil cores in 2009 and then again in 2019 to detect these differences in if there was a change in soil organic carbon after 10 years. And so what I'm showing you now is really the answer to that question. Did soil organic carbon change after 10 years across these different nitrogen fertilizer rates, these differences in residue return and nitrogen fertilizer application? So here you can see the change in soil organic carbon in terms of megagrams per hectare or tons per hectare after 10 years. So on net, what was the change? And you can see the change in the long-term N rates. So for the long-term, 30 kilograms of N per hectare, 56 kilograms of N, 87, 145, 218, and then 260. So the plots that receive that N rate consistently over 10 years. Now, in the 3 lowest N rates, where yield was lower, where we saw where residue return was lower, which we just saw, we had a small net decrease in organic carbon. Okay, let's call that between 0.5 to 2 tons per hectare reduction or megagrams per hectare reduction. This is very small. It would be very hard to detect this in a commercial soil test, like if you were just, sending it for nutrient analysis, looking for organic matter. It would not really move the dial. Very small, but it's there, a negative effect, okay, at those lower N rates. At the 3 higher nitrogen rates, where we had higher yields, therefore higher residue return, we have a net positive increase in organic carbon, a net positive. Again, not huge. We're talking about maybe 1 megagram per hectare or 1 ton per hectare change after 10 years. So we're talking about like 100 kilograms a hectare increase per year. Not huge, but it's there, okay? And I think what this data is suggesting is that at least in this part of Ontario, the study was done in Elora, so loam soil, higher nitrogen rates will not reduce soil organic carbon, okay? So we have a slightly positive effect, you could argue, although, if you do this statistical significance here, like Allison's done more recently, it's not necessarily significant, but there's certainly a trend. And you can certainly say higher nitrogen rates do not reduce soil organic carbon. That's certainly not the case. Now, this research really conforms to or is in concordance with a literature review, a meta-analysis of many different studies that looked at the effects of N fertilizer on soil organic carbon storage. And so the key points here are underlined. Nitrogen fertilizer increased soil organic carbon, but only when crop residues were returned to the soil. Okay, so that makes sense. And then carbon sequestration increased as more nitrogen was applied to the system and as rainfall or cropping system intensity increased. So in very dry environments, you would probably suppose you have low yield potentials, and so higher N fertilizer rates, you're not increasing yield, so you're not increasing residue, so you're not really increasing organic matter return. I just pulled out the main points of this meta-analysis. Again, many different data points, many different studies. 79% found that nitrogen fertilizer had a positive effect on soil organic carbon. And as more nitrogen was applied to the system, the differences in soil organic carbon storage between fertilized treatments and controls tended to increase, meaning as you increased N rates, you were probably increasing yields, increasing residue return, increasing organic carbon over time. Higher N rates were not associated with soil organic carbon depletion. So this idea that you're burning through soil organic matter when you add nitrogen fertilizer does not seem to hold water. Now, the effect of nitrogen fertilizer on organic carbon was higher in humid and temperate conditions, in other words, in areas where you had high yield potentials, was greater in coarser soils than in finer textured ones, which you could probably assume is due to just the amount of nitrogen mineralized by that soil naturally. So you could think that probably in coarser soils you don't have as much organic matter to start with, and so you don't have as much mineralization, so that crop will be more responsive to fertilizer N. So it needs fertilizer N more to get those higher yields, higher residue, more organic matter. And it was greater under rotations containing more crops per year or with corn as the main component of the cropping sequence. And that's purely an effect of the amount of residue in terms of weight left by a wheat crop compared to a corn crop. I mean, it's significant. It's a lot. You get a lot more residue with a corn crop left over after harvest than you would with, say, a small grain cereal.